Imagine you're behind the wheel of a high-performance dual-motor hybrid, right? You're out on an open road, and you decide to just really test it. You stomp on the accelerator, or maybe, a hazard pops up, and you just slam on the brakes.
Right, to aggressively regenerate that power.
Exactly. So in that split second, the motors demand just an absolute flood of power, or they try to shove a massive spike of kinetic energy right back into the battery.
Yeah, which is a huge stress event.
It is. But behind the scenes, deep inside the digital nervous system of the car, there is a fundamental conflict happening.
Oh yeah, a massive one.
Right. The motors are basically demanding more power than the battery can safely handle. So my question is, what actually prevents a catastrophic high-voltage failure right at that exact millisecond?
Well, for the driver, it's usually just a binary outcome.
Yeah.
It either ends in a catastrophic thermal event or a perfectly smooth stop.
Right. And we always expect the smooth stuff.
We do. We are totally conditioned to expect it. But achieving that invisibility, making that level of safety feel entirely natural, it requires a staggering amount of hidden engineering.
Yeah, and when you step into the world of automotive electrical engineering, you realize that illusion of simplicity is just a mask. It masks a diagnostic landscape that is essentially a war zone of physics.
But war zone's a pretty good way to put it, honestly.
Okay, let's unpack this. Today's deep dive is into a highly specific and highly critical engineering document. We are looking at the technical specifications of torque over limit via battery constraint.
Yes, specifically within the energy management in multi-motor coordination systems.
Right, and for the engineers listening, we are dissecting fault codes, DTC, P0A7F, and U0111.
Yeah, and to really understand the gravity of these specific codes, we have to look at their ASIL D safety rating.
Which is like the highest one, right?
It is. That's the Automotive Safety Integrity Level's absolute highest possible classification. Yeah. When a system carries an ASIL D rating, it means a failure presents an unacceptable risk of severe injury or even death.
Oh, wow. So we're talking about like uncontrolled acceleration or a total loss of regenerative braking.
Exactly. Or even the literal destruction of the high-voltage battery pack due to just massive overcurrent.
Right. It's the ultimate high-stakes environment. So our mission today is to unpack the 5 specific dimensions of how engineers handle this exact torque over limit fault.
And it's a huge topic.
It really is. We are going to explore the fundamental root causes of why the power conflict happens in the first place, then how the system architecture diagnoses the error in literal milliseconds.
The DFMEA design preventions.
That's the blueprint level stuff. And then the PFMA manufacturing controls on the assembly line. Okay. And finally, the brutal DVP and R production validation tests that these systems actually have to survive.
It really plays out like a detective story, honestly.
It totally does. A story where the culprit is the unforgiving nature of physics, and the defenses are just built from invisible lines of code and, perfectly tensioned bolts.
Yeah, and before we can really analyze the defensive architecture, we have to understand the weapons being deployed against it.
The root causes.
Right. In a highly integrated dual-motor high-voltage system, there are 4 primary root causes for this specific power constraint conflict.
Okay.
And they bridge both physical hardware degradation and digital software failures.
Well, the source material points to high DVDT electromagnetic interference, or EMI, as the first major root cause.
Yes. The EMI is a huge factor here.
So if we look inside the power control system, the PCS, we're dealing with silicon carbide or SiC MOSFETs.
Exactly, the SiC MOSFETs.
And these aren't your standard transistors, right? They are operating at switching speeds that seem almost violent.
Violent is the correct term for it, yeah.
Yeah.
These SiC MOSFETs are switching enormous amounts of power to drive the motors, and they do it by creating voltage transients of up to 10 kilovolts per microsecond.
Wait, 10 kilovolts in a single microsecond?
Yeah. Under extreme loads, you can even see switching edge rates of 50 volts per nanosecond.
That's insane. Generating a 50-volt swing in a billionth of a second, that has to create like an electrical shock wave.
It absolutely does.
Yeah, but how does that power switching noise cross over into the low-voltage communication systems? I mean, the high-voltage and low-voltage systems are supposed to be physically isolated, right?
Well, they are isolated physically, but when components are packed that densely into a power control system casing, you introduce parasitic capacitance.
Okay, wait. What is parasitic capacitance exactly?
So this isn't a physical capacitor that you solder onto a circuit board.
Right.
It's stray capacitance formed simply by having 2 conductors really close to each other, separated by an insulator, like a heatsink and a control board.
Ah, I see. So the proximity alone creates it.
Exactly. And that high-frequency common mode noise basically bridges the gap through that parasitic capacitance.
Oh, wow.
Yeah, it injects itself directly into the low-voltage signal lines, specifically the CNFD network.
Which is the main communication backbone of the whole vehicle.
Right. It's the nervous system.
So the battery management system, the BMS, it's monitoring cell temperatures and state of charge, right?
Right.
And it tries to broadcast a critical message like, hey, thermal limits reached, reduce power draw immediately?
Yes, but that data frame hits this massive wave of common mode noise.
Right. And I assume this leads to CRC checksum errors where the packets are just mathematically corrupted.
Well, exactly.
Yeah.
The CAN transceiver sees the corrupted frame,
Yeah.
fails the cyclic redundancy check, and just discards the message entirely.
It just drops it.
Yeah, it drops it. And because the motor controller didn't receive the updated stricter power limit, it defaults to the last valid message it received.
Oh, I see. So it continues operating under an outdated loose power limit.
Right. It's pulling massive currents and completely violating the battery's real-time safety boundary.
Simply because of a communication blackout caused by the motor's own electrical noise.
Yeah.
That is wild.
It is.
Okay, so the second root cause shifts from electrical interference to magnetic physics. The notes call it inductance saturation and mathematical mismatches.
Yeah, this one is fascinating.
Because in standard motors, you deal with thermal limits, but under deep magnetic saturation, the actual inductance of the metal itself changes, right?
It changes drastically, yeah.
Yeah.
During extreme acceleration or massive regenerative braking, the inverter pumps just massive phase currents into the motor stator core to generate that instantaneous torque.
Right, to get the car moving or stopping fast.
Exactly. And the iron core consists of these microscopic magnetic domains. As you push more current, those domains align to carry the magnetic flux.
Okay, makes sense.
But there's a physical limit. Once all the domains are aligned, the core is fully saturated.
Like a soaked sponge that just can't hold any more water?
That is the perfect analogy.
Yeah.
At that exact moment, the physical inductance, specifically the direct and quadrature axes known as L and LQ, it just plummets.
And it doesn't just drop linearly, right? It falls off a cliff in a highly nonlinear curve.
Right, it's a huge sudden drop.
So how does the field-oriented control algorithm, the software calculating the voltage vectors, how does it even begin to compensate for a nonlinear drop like that?
Well, that's the problem.
Yeah.
If it's using a static mathematical model, it's going to be completely blind to the physical reality of that saturated metal.
It just doesn't know the sponge is full.
Exactly. The algorithm is effectively flying blind. The math model assumes a specific inductance value to calculate the necessary voltage to hit the target torque.
Okay.
So when the physical inductance collapses, that applied voltage suddenly draws a vastly higher actual DC current from the battery than the math predicted.
Oh, wow. So without some kind of complex real-time compensation, you get a massive power limit conflict.
Exactly. The software calculates that it is operating safely within, say, a 300 kilowatt limit. But the physical reality is that the inverter is actually pulling 400 kilowatts.
Which is stressing the battery cells right toward thermal runaway.
Yes, it's extremely dangerous.
So the software thinks it's sipping water, but the physical hardware has basically opened a fire hydrant.
That's exactly what's happening.
Okay, the third root cause brings us back to software. Priority inversion and task scheduling latency.
Yeah, this is a classic operating system bottleneck.
Right, but the consequences here are critical, not just a frozen app on your phone.
No. Not at all. It fundamentally comes down to resource contention within the real-time operating system, or RTOS.
Okay.
So to maintain smooth rotation and maximize motor efficiency, the motor control algorithms operate at the absolute highest interrupt priority.
Because they have to be perfectly timed.
Right. They are executing a control loop every 100 microseconds.
Wow, that's fast.
It is. The BMS updates, however, the battery limits, those are transmitted over the CAN network at a much slower rate, typically every 10 milliseconds.
Oh, I see. So it has like a high-frequency trading algorithm running on a dedicated fiber optic line, while the risk management department is trying to send crucial stop-loss warnings via a dial-up modem.
That captures the asymmetry perfectly. Yeah. And under normal conditions, it works fine.
Right.
But during moments of high CPU load, perhaps the primary microcontroller is simultaneously handling a complex torque vectoring calculation, an ABS intervention, and standard diagnostics all at once.
Right. The computer gets busy.
Exactly. And a lower priority task, holding a resource lock, can actually block a higher priority task. This is priority inversion.
So the software just gets completely bottlenecked.
Yes. It gets bottlenecked and fails to unpack the new CAN frames from the battery.
And the motor controller, which is running at its blistering 100 microsecond loop, just keeps executing commands based on the stale limits.
Right, entirely ignoring the slower bottleneck warnings from the BMS.
Because it hasn't read the new email, basically.
Pretty much, yeah.
Okay, so we've established that the software can get bottlenecked and electromagnetic shockwaves can corrupt the data. But what happens when the hardware itself is actually lying to the software?
Oh yeah, this is the physical wear aspect.
Yeah, I was looking at the notes on physical busbar wear, and the fourth root cause, fake voltage drops. This one fascinates me because it stems from something as simple as a bolts coating.
It really is that simple sometimes.
Yeah.
So the high voltage bus bars are these thick copper or aluminum bars, right? They're responsible for carrying hundreds of amps between the battery, the inverter, and the motors.
And these connections have to be secured with heavy-duty bolts.
Exactly. But if a bolt lacks a specific anti-corrosion phosphate, coating its friction coefficient is fundamentally altered during the initial factory assembly.
Okay, so when the automated torque wrench tightens it on the line, what happens?
Well, it reaches the target torque prematurely because the threads are binding up.
Oh, I see. So it's not actually clamping the plates together with enough force.
Right. It's achieving the torque spec on the wrench, but failing to achieve the necessary axial tension, the true clamping force.
And over thousands of miles of road vibration and, extreme thermal expansion and contraction, that suboptimal joint just loses whatever residual clamping force it had.
Yeah, it loosens up. And when a connection carrying 500 amps loosens the contact resistance at that specific joint spikes.
Right, because there's less metal touching metal. And according to Ohm's law, a spike in resistance with massive current running through it results in a massive voltage drop across that loose connection.
Exactly. Plus a lot of I²R heat generation.
Which is bad news.
Very bad. The motor controller relies on local sensors to measure the DC bus voltage. But because of the voltage drop across the loose busbar connection, the controller reads a lower voltage than the battery is actually outputting.
Oh, wow. So since power is calculated as voltage multiplied by current, this artificially low voltage reading causes the software to calculate the instantaneous power incorrectly.
Right. It triggers a false torque over limit conflict. It initiates a massive diagnostic panic, all tracing back to just a microscopic lack of phosphate on a single threaded bolt.
That is incredible. A single bolt missing its coating can trigger an ASIL D diagnostic panic.
It really highlights how interconnected the mechanical and digital domains are.
It totally does. So we are dealing with a literal diagnostic war zone here. Common mode noise-destroying CAN packets, nonlinear inductance saturation throwing off the fundamental math, priority inversion paralyzing the RTOS, and oxidized bolts lying to the voltage sensors.
It's a lot to defend against.
It is. So knowing all the complex ways the system can be compromised, how does the vehicle's architecture actually diagnose and neutralize these threats before the lithium-ion cells suffer irreversible damage?
Well, the defense relies on a rigid, highly orchestrated diagnostic architecture. And the most critical constraint here isn't computation power, it's time.
Time.
Yeah, the system operates within a strict 60-millisecond window.
Wow, that's fast.
In functional safety terms, this is known as the fault-tolerant time interval, or FTTI.
Okay, but why exactly 60 milliseconds? Is that just an arbitrary standard?
No, it's highly specific. It is the calculated threshold before massive overcurrent causes the internal temperature of the lithium-ion cells to reach a point of no return.
So any longer and you risk thermal runaway.
Yep. Exactly. Thermal runaway or severe irreversible degradation of the battery contactors. The system must recognize the fault, process it, and physically halt the overcurrent all within that 60-millisecond window.
Okay, so what is the first layer of this 60-millisecond defense?
It's called power plausibility diagnostics. Basically, if the data from the CAN bus can't be trusted due to noise or latency, the system has to cross-examine its own physical reality.
It has to double-check the math.
Exactly. It performs a continuous independent energy balance calculation.
How does it do that?
It calculates the physical DC power leaving the battery. So it multiplies the DC voltage and DC current, and then it cross-references that against the AC electromagnetic power being generated at the motor.
Ah, okay. So by multiplying the three-phase AC voltages and currents and factoring in power factor and mechanical losses.
Exactly. It is actively looking for a residual error, a mismatch between the energy entering the inverter and the energy leaving it.
And the response to finding an error is tiered right, because you don't want to violently shut down the powertrain on a busy highway if it's just a minor cento fluctuation.
Right. The response is very carefully calibrated. If the calculated physical power exceeds the BMS dynamic limits by more than 5%, and that condition persists for 10 milliseconds to filter out any transient noise spikes, it triggers a level 1 warning.
Okay, a level 1 warning. What does that actually do?
The system logs the POA7F fault code and initiates a controlled torque derating. It ramps down the motor torque at a smooth rate of 500 newton meters per second to bring the power draw safely back within the envelope.
Okay, that sounds reasonable, but if the discrepancy is massive, say the inductance saturation caused a sudden huge current spike, a smooth 500 newton meter ramp down isn't going to save the battery fast enough.
No, it won't. And that triggers the level 2 fatal alert.
Oh, okay.
If the power exceeds the safety limit by 15% or more for just 5 milliseconds, the system determines that software control is either lost or totally insufficient.
Wow, 5 milliseconds is nothing.
Right. So it bypasses the complex motor control algorithms entirely and utilizes hardware-level logic to execute an immediate physical shutdown of the power stages.
But wait, relying on the same processor that might be experiencing priority inversion to trigger the shutdown seems like a major single point of failure.
It would be yes, which is why they don't do that.
Right. The notes mention a duo-checker dual-core architecture, so I assume the checker is physically segregated from the doer to prevent a shared software crash.
Yeah, the architecture is completely asymmetric and functionally isolated. The main microcontroller core, the doer, is responsible for the heavy computational lifting, the field-oriented control, the sensor processing, the torque vector.
All the complex driving stuff.
Right. But running alongside it is a completely independent subcore, the checker.
So does the checker just run a redundant version of the FOC algorithm to, like, compare answers with the doer?
No, actually. Because if there is a fundamental flaw in the FOC algorithm's handling of, say, deep saturation, both cores would generate the exact same flawed answer.
Oh, that's true. They'd both agree on the wrong math.
Exactly. So instead, the checker operates exclusively on fundamental laws of physics, like the conservation of energy and stator flux limits.
Oh, that's brilliant.
It passively monitors the raw sensor inputs and the doer's output commands.
So it's just watching.
Just watching. But if the checker calculates that the doer's requested PWM signals will violate the physical safety envelope of the battery, it doesn't even request a software override.
What does it do?
It utilizes a separate system basis chip to physically sever the gate drive signals to the CPIT MOSFETs in under 100 microseconds.
Under 100 microseconds. That is an incredibly aggressive intervention. The checker just yanks the hardware power cord, basically, before the fatal command can even leave the processor board.
Yes, it cuts the hard line.
But let's say the issue isn't a bad command from the doer, but a total loss of CAN communication for 50 milliseconds. Like the BMS just goes completely dark. What is the ultimate safe state the system defaults to then?
Well, the system must fall back to one of two ultimate safe states. And it depends entirely on the kinetic energy involved at that moment, specifically the rotational speed of the motor.
Okay, so speed is the deciding factor.
Right. If communication is lost at high speed, which is generally defined as the motor spinning at 7,200 RPM or greater, the system executes a stepwise active short circuit, or ASC.
Wait, an active short circuit? Intentionally commanding a short circuit in a high-voltage powertrain sounds completely counterintuitive. Why not just open the contactors and, completely disconnect the motor from the battery?
You'd think so, right? But because a permanent magnet synchronous motor acts as a massive generator when it's spinning, you can't just disconnect it.
Oh, right, because the magnets are still moving.
Exactly. If you simply open the circuits at 12,000 RPM, the back electromotive force, the unregulated voltage generated by those spinning magnets, will vastly exceed the battery's maximum voltage rating.
Oh, wow.
Yeah, that back EMF will punch right through the inverter's freewheeling diodes, surge into the DC bus, and literally destroy the battery pack.
Okay, so by initiating an active short circuit, you are essentially trapping that massive regenerative energy.
Yes, but the execution has to be perfect. First, it shorts just 2 of the 3 motor phases for 1.5 milliseconds.
Why just 2?
This asymmetric short acts as a buffer. It dissimates the initial inductive spike safely, and then immediately after that 1.5 milliseconds, it slams all 3 phases into a dead short.
So you are intentionally turning the motor's copper windings into a massive heater? You're sacrificing the thermal capacity of the stator mass to absorb all that kinetic energy and prevent it from reaching the battery.
That's it, exactly. It is a highly localized thermal event designed to prevent a system-wide catastrophic failure.
That is why...
By shorting the phases, the generated electrical energy circulates entirely within the motor windings, just converting to pure heat.
And this successfully clamps the DC bus voltage.
Yes, it keeps it well below the critical 720-volt threshold, perfectly shielding the battery.
It is a brutal but honestly brilliant trade-off. And I assume at lower speeds, the back EMF isn't high enough to threaten the battery, so the strategy just changes.
Right. Below 2,000 RPM, the generated back EMF falls safely below the battery voltage naturally. So the system triggers an active open circuit, or AOC.
Which just means letting go.
Yeah, it ceases all gate drive signals, dropping the torque output to zero, and allowing the vehicle to freely and safely coast to a stop without inducing any electrical drag at all.
Okay, we've seen how the 60-millisecond architecture detects and reacts, but relying purely on reaction time is really the last line of defense. The true engineering happens long before the car is built right, during the DFMEA.
Yes, the design failure mode and effects analysis. This is where engineers fortify the actual blueprints to eradicate vulnerabilities at the component level.
Right. The DFMEA shifts the paradigm from reaction to prevention. So let's look at the software timing errors. The priority inversion we discussed earlier. You just cannot tolerate communication desynchronization in an ASIL D system.
No, you absolutely can't.
So how do they guarantee synchronization on the circuit board to prevent the doer and the checker or the key and transceiver from just drifting out of phase with each other?
They enforce synchronization at the lowest possible level, the hardware oscillator level.
Okay.
In the PCB layout, the primary microcontroller, the checker core, and the communication ICs are all driven by a shared, highly stabilized hardware clock source.
So they all share the exact same physical heartbeat.
Exactly. By locking the entirely distinct subsystems to a single heartbeat, they constrain the phase error between components to less than 0.5 degrees.
Wow, less than half a degree of drift.
Yeah, it mathematically eliminates the possibility of internal timing drift, causing a data bottleneck.
That makes total sense.
Yeah.
And what about the electromagnetic warfare happening inside the casing? We talked about those CCAW MOSFETs generating that violent 10 kilovolt per microsecond shock wave.
Like the EMI.
How does the DFMEA isolate the low-voltage communication lines from that common mode noise?
Well, the blueprint specifies 2 layers of really aggressive isolation. First, they utilize specialized digital isolator chips for the communication buses.
Okay.
These chips are rated for a common mode transient immunity, or CMTI, exceeding 100 kilovolts per microsecond.
Exceeding 100 kilovolts. That CMTI rating essentially means the isolation barrier within the chip can reject voltage spikes that fast without letting any of the noise couple across into the clean side of the circuit.
Exactly. It's a massive physical barrier. And alongside the high CMTI isolators, the design also mandates the inclusion of common mode chokes on the physical CAN lines.
What does a common mode choke do?
It's a magnetic component. It allows differential signals, which is the actual data you want, to pass unimpeded. But it presents massive impedance to common mode noise.
Ah.
These chokes actively suppress the high-frequency switching noise by an additional 40 decibels. It virtually guarantees the physical integrity of the data frames.
Okay, I want to transition to how they handle temperature drift, because an automotive powertrain is an incredibly hostile environment. We aren't dealing with server racks in a climate-controlled room here.
Not at all.
These components are bolted to a vibrating transmission casing that can reach 150 degrees Celsius, and heat fundamentally alters electrical resistance and capacitance, right?
Oh yeah, thermal drift is a massive source of diagnostic errors.
Right.
So to prevent analog sensor circuits from drifting and reporting false voltage drops, the DFMEA mandates Class 1 COG ceramic capacitors and ultra-precise thin film resistors in all the critical measurement pathways.
Right, because most standard capacitors like X7R types, they lose a huge percentage of their capacitance as they heat up.
They do. But the COG dielectric material is specifically engineered to maintain a flat capacitance curve regardless of thermal stress.
So it measures exactly the same at 150 degrees as it does at room temperature.
Exactly. But hardware stability is really only half the solution. The other half addresses the motor's magnetic saturation.
Ah, the soak sponge scenario, where the FOC math deviates from reality.
Right. The software is actually designed to dynamically adapt to the physical degradation of the motor.
Wait, how does a static algorithm map a dynamic nonlinear physical change in real time?
It's really clever. It utilizes a combination of 2D lookup tables that are mapped across the entire temperature and current operating range. And it combines that with active parameter estimation using recursive least squares algorithms.
That sounds intense. How does it get the data for that?
The inverter actually constantly injects tiny high-frequency test signals into the motor phases during normal operation.
Just feeling out the metal base.
Exactly. By analyzing the current response to those tiny test signals, the software recalculates the physical state of resistance and inductance in real time. It tracks it all the way up to 150 degrees Celsius.
So it constantly updates its own internal physics model. It realizes the metal is saturating and alters the FOC math on the fly, completely mitigating the mathematical mismatches that cause the torque overlimit fault.
Yep, it's totally dynamic.
That is an incredibly elegant solution. But even the most robust blueprint is useless if the manufacturing process itself introduces defects, right?
Oh, absolutely. Which brings us to the PFMEA, the process failure mode and effects analysis, the controls on the factory floor.
Right, because the manufacturing controls are designed to essentially eliminate the human element and physical variance.
Right. Let's return to the root cause of the loose bus bar bolt causing a false voltage drop.
Okay.
You can't rely on a technician with a manual click wrench to achieve perfect tension on thousands of critical high-voltage joints. It's just not repeatable enough.
Because friction varies, right? A bolt might click the wrench early just because the threads are slightly dirty, leaving the actual joint dangerously loose.
Exactly. So the notes detail torque angle closed-loop servo control on the assembly line.
Walk me through the mechanics of that. How is that different from a normal torque wrench?
Well, a standard torque wrench only measures rotational resistance. A torque angle servo tool measures both rotational torque and the precise degrees of rotation. The system drives the bolt to a very low initial snug torque just to seat the plates together flat. Then it monitors the exact angle of rotation required to reach the final yield torque.
Oh, I get it. By measuring the angle, it is calculating the actual physical stretch of the bolt, the elastic deformation.
Exactly. And that stretch is what provides the true permanent clamping force, not the twisting friction.
That's brilliant.
This closed-loop control guarantees the axial preload on every single busbar connection is within a plus or minus 3% variance. It's incredibly precise.
Furthermore, to prevent the friction issues that cause binding in the first place, the line utilizes optical character recognition or OCR camera systems, right?
Yes, the OCR systems scan every individual bolt before insertion to verify the presence of that dark anti-corrosion phosphate coating we mentioned earlier.
So if a bolt is just bright, shiny metal indicating it missed the coating process at the supplier, the camera flags it.
It flags it and physically prevents the robot from driving that specific fastener.
Wow, it's a multi-layered verification process, and I'm sure they apply even more stringent controls to the circuit boards themselves. Because you can have a perfectly tightened bolt, but if the solder joints underneath the primary microcontroller fail due to vibration, you still lose the entire safety architecture.
Exactly. The source material specifies the use of 3D automated X-ray inspection, or AXI, combined with scanning acoustic microscopy.
So they are literally looking through the silicon to inspect the solder balls on the BGA, the ball grid array.
Yes, they are.
What specific defect are they hunting for with the X-ray?
Ovoids. Microscopic air bubbles that get trapped inside the molten solder during the reflow oven process.
Okay.
The PFMEA sets an uncompromising standard here. The total voiding rate across the entire array must be strictly less than 5%, and no single solder joint can contain a void larger than 1% of its total volume.
Wait, why is a microscopic air bubble so critical to functional safety? That seems almost pedantic.
It is because of the thermal expansion mismatch. You have the silicon chip, the solder, and the fiberglass circuit board. As the inverter heats up to 150 degrees and cools down to sub-zero temperatures thousands of times over its lifespan, those materials all expand and contract at completely different rates.
Oh, right. So they're pulling and pushing against each other.
Exactly. This induces massive shear stress on the solder joints. A void acts as a stress concentrator. Over time, that tiny void propagates into a micro crack, basically severing the electrical connection.
And a severed pin on the microcontroller could result in a sudden total loss of sensor data, triggering a catastrophic fail-safe response on the highway.
Exactly.
So by utilizing 3D AXI to enforce that crazy 1% voiding rule, they ensure the structural integrity of the silicon's connection can survive a decade of thermal shock?
That's exactly why they do it. And after the perfectly coated bolts are tensioned and the X-rayed circuit boards are integrated, the fully assembled power control system reaches the end-of-line or EOL test stand.
And this isn't just a passive diagnostic check, right? They intentionally subject the unit to targeted fault injections to prove the 60-millisecond architecture actually functions in reality.
Right. They simulate the absolute worst-case digital scenarios right there on the factory floor.
So the automated test equipment might digitally sever the CN communication lines, simulating a total BMS blackout, or instantly drop the simulated power limit to 0.
Yes. And the system is placed on a rigid timing threshold during this test. The newly manufactured unit must detect the injected fault within the 10-millisecond plausibility window, And then it must successfully command the safe state, like verifying the gate drive signals for the active short circuit within the remaining 50 milliseconds.
Wow. So if the unit takes, say, 62 milliseconds to process the fault, what happens?
The manufacturing execution system, which is the software managing the factory floor, it registers a critical failure and physically locks the assembly rail.
It locks it.
Yes. The automation will not release the pallet to the packaging station. The unit is physically quarantined.
It completely automates the quarantine of non-compliant hardware. That is rigorous. So we've covered the physics, the architecture, the blueprint design, and the microscopic manufacturing controls. This leads us to the final dimension, DVP&R, or the Design Verification Plan and Report.
Yes, the final gauntlet.
Right before a new vehicle platform is ever cleared, for mass production prototype units must survive a gauntlet of environmental and digital torture tests.
The DVP&R phase is where theoretical engineering is finally validated against physical extremes. The first primary test is often referred to informally as shake and bake. It's a brutal, accelerated life test.
Okay, shake and bake. The unit is mounted inside a specialized environmental chamber on a multi-axis shaker table, right? And it is subjected to aggressive random vibration profiles mimicking a lifetime of harsh road impacts.
Wow.
And while it's violently vibrating, the ambient temperature inside the chamber cycles endlessly between negative 40 degrees Celsius and positive 125 degrees Celsius.
Yes, and this test runs continuously for over 1,000 hours.
Over a month.
Over a month. And to make it a true operational test, they cycle massive high-voltage currents through the system the entire time. They're actively trying to induce the thermal expansion microcracks and joint loosening we discussed earlier.
Over a month of continuous freezing, boiling, shaking, and high-voltage loading. What are the engineering pass-fail metrics after the 5 hours are up? They can't just look at it and say, yep, it works.
No. They tear the unit down completely and measure the physical degradation. Those torque angle bus bar bolts we talked about. They cannot have lost more than 5% of their initial clamping force.
Wow.
Furthermore, they measure the contact resistance across the high-voltage joints. The resistance cannot have increased by more than 1.2 million ohms from its pre-test baseline.
1.2 thousandths of an ohm is the maximum allowable degradation after 1,000 hours of torture. The tolerances are microscopic.
They have to be.
But surviving the physical world is only one hurdle, right? The DVP&R also requires surviving electromagnetic warfare.
Oh yeah, this test is intense. While the inverter is driving a dynamometer load spinning the motor at maximum speeds approaching 12,000 RPM, test engineers basically bombard the casing and the wiring harnesses with massive external high-frequency radiation.
Just blasting it.
Yeah, they utilize bulk current injection clamping inductive probes directly onto the communication lines to actively force heavy RF noise right into the CAN network.
They are aggressively attempting to jam the car's digital nervous system, trying to force those CRC checksum errors we talked about at the beginning.
Exactly.
And the passing grade for surviving this electronic warfare attack.
A 0% frame error rate. The CMTI isolation and the common mode chokes must prove they can reject the injected noise completely. Not a single piece of data is allowed to drop. The torque command data must remain perfectly stable despite the extreme external interference.
That is incredible. Okay, here's where it gets really interesting. The final exam is the real-time simulation utilizing an FPGA ASIL rig, hardware in the loop powered by field programmable gate arrays.
Yeah, because a standard computer processor is just too slow to simulate a high-voltage powertrain accurately enough for these tests. FPGAs process the complex differential equations of motor physics in nanoseconds.
So the real physical motor controller is plugged into this FPGA supercomputer.
Right.
The rig feeds the controller analog and digital signals, basically tricking it into believing it is driving a fully loaded vehicle down the highway at maximum speed.
Exactly. The physical controller thinks it's doing 150 miles per hour, pulling maximum current, and then the engineers initiate the ultimate nightmare scenario, the load dump.
Oh man, the load dump. So they digitally simulate the catastrophic failure of the main high-voltage contactors. The simulated battery pack instantly disconnects while the motor is spinning at 12,000 RPM.
Right, so the back electromotive force from those spinning magnets suddenly has nowhere to go. The battery, which acts as the electrical shock absorber for the whole system, is just gone.
So the voltage is going to spike instantly.
In that exact moment, the physical controller must flawlessly detect the loss of the DC link and execute the stepwise active short circuit.
And the FPGA rig monitors the real-time reaction to see if it did it right.
Yes. The test is considered a pass only if the controller shorts the phases fast enough to ensure the internal DC bus voltage never crosses 720 volts. And the maximum short-circuit phase current has to remain under 550 amps.
Proving that the architecture can autonomously absorb the kinetic energy of the motor without destroying its own power stages.
Exactly.
So what does this all mean for us? Let's take a step back and look at the depth of this 5-layer engineering discipline.
It's massive. We started by analyzing the chaotic root causes, right? Violent electromagnetic shock waves corrupting vital safety data.
And the physical iron of the motor saturating and basically breaking the software's mathematical assumptions.
Right. Then we saw how the 60-millisecond dual-core architecture relies on an independent checker running pure physics algorithms to sever power.
We explored how the DFMEA redesigns the blueprints to include hardware clock synchronization and heat-immune ceramics.
We walked the assembly line, where automated servo tools and 3D X-rays enforce absolute physical perfection.
And finally, we saw how the DVP-R validates all of those theories through 1,000-hour vibration chambers and nanosecond accurate FPGA simulations.
It really is a journey.
It is. It totally reframes the entire experience of driving an electric vehicle. You know, when you aggressively step on the regenerative brakes, you aren't just engaging a simple mechanical system.
No, you're relying on a synchronized ballet of isolated processors, predictive thermal algorithms, and verified solder joints, all executing perfectly in a fraction of a millisecond to manage lethal amounts of electrical energy.
It is an invisible, heavily fortified safety net. But looking at how these systems currently operate, it raises a fascinating question about where automotive functional safety is heading next.
It really does.
Because at the very end of our source notes, there is an addendum discussing the use of advanced Python simulation tools. Engineers use these tools to model the complex electrothermal coupling of the system, mathematically deriving the absolute perfect time window to filter out transient noise without reacting too late.
Right. But currently, they hard code a 10-millisecond plausibility delay. It's a static rule.
Exactly. It's static. But the integration of predictive AI and machine learning into these microcontrollers is imminent.
Oh, yeah, it's definitely coming.
Right. So if we are currently relying on static delays and a 60-millisecond reaction time to mitigate a catastrophic constraint violation after the hardware begins to fail, what happens when the powertrain integrates real-time predictive models?
That's the big question.
Could the motor controller utilize localized AI to continuously calculate the thermal trajectory of the battery based on, driving behavior in ambient conditions?
It would represent a fundamental shift from a reactive safety architecture to a purely predictive one.
Right.
Instead of relying on a 60-millisecond emergency shutdown when the limit is breached, the AI could predict the thermal bottleneck 3 seconds in advance. And it could imperceptibly adjust the torque vectoring to avoid the constraint entirely.
3 seconds before the driver even touches the pedal, the system has already recalculated the physics and smoothed out the power demand. The transition from surviving the failure to mathematically guaranteeing the failure never occurs in the first place.
It's the future of functional safety.
It is. Let that marinate until next time.